It's my pleasure to present you Ayan Chaudhury. Ayan was working in the ROMI project before. He's currently assistant professor at the Indian Institute of Kharagpur University. Ayan is going to present a tool that he developed and how to create a point cloud out of a virtual plant model using LPI tools. Ayan.
Okay, thank you, Christoph, for the introduction. So, okay, today I will talk about the point cloud generation from L system models, or more specifically, how to generate level point cloud from virtual plant models that were built using L system models. Okay, so before going to the demo and all these type of technical things, so I will give you some background. Why do we need this, and how do we achieve this? Okay, so why do we need level datasets? So first of all, level datasets are of immense importance for plenty of tasks in machine learning. Level data means ground truth data. Okay. So for example, to evaluate the performance of an algorithm, so you will need a level data, because without level data, you don't know if your algorithm is performing well or not. So somewhere you have to have some ground truth. Also, in order to compare with the other state of the art, so you also have to have some common comparison ground. So in order to do this, you also need ground truth data. And this type of ground truth data is absolutely important for any case of machine learning, like a supervised machine learning models, for the case of 2D, 3D, or anywhere. Okay. So and nowadays, so when I'm talking about machine learning models, so basically you can think of deep learning and non-deep learning in both type of model. Okay. But in recent years, there has been a lot of progress in deep learning based machine learning models. So, but the problem with the deep learning models is that they are very data hungry. So that means they need a lot of training data. Like hundreds and thousands of level data need to be fed to the network, and then the network can perform well depending on the application and depending on the architecture. So in general, this level data and all these things are very much done manually. However, which is pretty hard for the case of plants for generating this type of manual data for a large scale analysis. So just imagine that you are photographing or scanning a large, like hundreds and thousands of plants, and you are annotating each of the leaves, each of the stems, and all the roots and flowers, everything separately. So that's a huge tedious job. So that's why it's there is a real lack of annotated data in the plant phenotyping community at the current moment, just because of the extremely important manpower and also the time factor. Okay. So, however, there has been a lot of 2D data sets proposed in the last few years. So annotation of 2D data is relatively easier because there are lots of tools available actually, where you don't have to actually annotate each pixel separately. So that with the tools, actually, sometimes it's easier. Okay. So for example, this Arabidopsis rosette dataset in 2016, an oil radish dataset. So that was published in 2019. And also in recent years, there has been some progress of using synthetic data. For example, these data sets are of Arabidopsis rosettes, so that were created using generative adversarial network, and also using the procedural model like L system based approaches. So the bottom one actually is from the L system based model. So these are also created to create realism, and so that actually we can have a replacement for the real data. However, the problem is that although in the 2D case, actually, there has been quite a few data sets for this type of synthetic data. So there is almost nothing for the case of 3D, actually. Only recently, there has been some data sets have been proposed. For example, the Rosebush dataset. So that was published in 2020, actually. So where actually some of the Rosebush models were created and they were actually annotated. Although the geometric plant model is not available publicly, only the annotated data is actually available. Okay. Also, there are some quite like a couple of data sets, other data sets available actually, which are annotated actually, sometimes manually or sometimes using some other methods. So there are lots of challenges basically for creating 3D point cloud data sets, as I mentioned just now. So first of all, it needs in order to create 3D point cloud data set, you have to capture the data. or you have to create the point cloud of an existing object, which is a plant. So you need expensive hardware to perform scanning. For example, if you have a laser scanner, actually, so laser scanners are pretty expensive if you really want to scan it and then actually obtain a point cloud from it. Also, there is a problem with the occlusion while scanning, because just consider it very dense and leafy plants. So even if you scan from a very close angle, actually, so there are always some parts which is at the interior part of the plant, and basically getting those points is very hard. So occlusion is an inevitable factor, and there is no way actually you can like get rid of this thing if you just actually scan from outside, because the laser beams will never reach those parts of the plant because they are occluded by the outer parts. Also, even if you do like handle the occlusion problem, or if your plant is not leafy or not dense at all, still you need a multiple view reconstruction for the full 3D model of the plant. Because usually what happens when you scan an object or a plant in our case, so you scan from multiple directions, and all these scans are basically registered together using some like a pairwise registration. So that means you register scan 1, scan 2, and then get the result, and register with scan 3, get the results, and with scan 4, and so on and so on. And eventually you get a 3D point cloud model of the whole object. So, but this is also a tedious process. That means you have to have a very good reconstruction algorithm to get the full 3D point cloud model of the plant. Otherwise, when you scan from one direction, it's just a single view. Okay, so that means in order to get the full 3D point cloud, actually you need to have a reconstruction technique. Sometimes people also use SFM techniques, which is called the structure from motion technique, where actually you take photographs from different directions, like a 2D photographs, and then basically estimate the camera parameters and eventually create the 3D point cloud model. But sometimes these methods are very noisy, and also there is a problem of scale factor, because this scale factor actually might not match the actually original object. So these methods have lots of drawbacks with these SFM techniques. And of course, if you try to do the manual leveling of the data, there are lots of chances of error, specifically for the case of 3D point clouds, actually. So there is a need to find an alternate solution for these cases. So this is the motivation of our work, actually, where actually we address this problem and focus on geometric plan models, so that can come to the rescue for actually handling these type of problems, actually. So virtual plan. So what is a virtual plan? So basically, in the virtual plant, actually, we don't need any real plant at all. So this is fully a computer generated model. Okay. So with this type of model, so there are different approaches of doing this. So procedural approach, or as I mentioned, L system is one type of procedural approach that has been very successful in the last few decades for plant modeling in the computer graphics community, and also like a plant modeling community. So in this case, basically, we can generate a large number of diversities using the inherent stochasticity of the model. So basically, when we actually generate the plans, so we impose the stochasticity, for example, the number of branches, the number of leaves, the branching angle, like even the divergence angle, and all these type of things, we usually impose stochasticity in it. So that means every time actually you launch this model, so it will create a new model actually, because of the stochasticity. It's random. Okay? So that means if you launch the model by 1,000 times, so then actually you can create 1,000 diversities. So there are actually infinite diversities that actually you can create by using the randomness, inherent randomness inside the models. And also, you don't need a manual annotation for this, because when you create these models, actually you know which part is leaf and which part is stem and which part is flower, or whatever organ it is. So that means there is no chance of leveling error. So it's 100% reliable. Okay. So that means virtual model, if we can create a geometric model of a plant, then actually we can rely 100% on it in the leveling aspect, or in terms of like organ detection, or organ aspect actually. But the question is that how to get the point cloud from these type of models, because these type of models are actually, because you see the left hand side figure, so this is actually like a like the primitives. Like means basically these are actually modeled using primitives like cylinder, circle, triangle, and all these type of things. And you see the colors and all these things. So these are basically just a rendering thing. The lighting effect and color is a typical computer graphics applications and nothing else. But just consider the geometry. Basically, you get the primitives with different types of basic geometrical primitive. But how to get a point cloud from here? So surprisingly, this type of problem has never been addressed before. Although this modeling, this type of plants or this type of geometric modeling has been very popular in the community for decades, but nobody has ever attempted to extract level point cloud automatically from this type of virtual models. So in this work, actually, we do the same. Actually, we generate sample, or we basically sample level point cloud from this type of virtual models. So this is an example of a Arabidopsis plant, which is a model plant in biology, and this is the corresponding point cloud where actually you see that the leaves at the bottom of the rosette leaves are red, and the stems are basically green, and the other parts are basically blue. But this is just an example. So it is possible to level everything. So it is possible to level each of the branches, or each of the fruits, even each of the petal of the flowers, everything to have a different level. So everything is fully under control. So it depends on how do you model your plant. So whatever is your is your application demanding, so you can generate the point cloud data accordingly. For example, if you want to have a semantic segmentation, so then basically this type of leveling is sufficient. But if you want to have instance segmentation, for example, where each instance of a same object actually will have different level, then actually probably you need to customize it more. So that means you have to have a different level for each of these organs actually. So these are all actually possible within to do in this type of models actually. So what do we need to create level point cloud actually from a virtual model? Okay, so first we need basically two things. So first, the virtual model of the desired species. So of course, this is the most important thing, because we need to have a geometric model without which we cannot do anything. So we assume that the virtual model of the desired species, for example, let's say we are trying to sample generate data for tomato plant. So we need to have a model of a tomato plant. If we want to have a Chenopodium model, then we need to have a virtual plant of Chenopodium plant. Okay. And also in our case, since all of our implementation is done on LPI environment, so we assume that the virtual plant model of the species of interest, that's actually available in LPI environment, or the LPI code is available. Okay, so this is first assumption. And second assumption is that we need to know the L strings of the model. Okay. So, but even if we don't know what is the L string model. For example, if you don't know how to model the geometric plant actually, then but say that you have the model, you have got it somewhere, but still it is possible to print the L strings or see the L strings. So that means if you don't have to know anything with about the detailed knowledge of the geometric plant model, you just need the L strings of the model actually, and it is even if you don't have it, this can be printed easily. So that's it. If you have these two things, then that's all we need. We don't need anything else. And from this, actually, it's possible to create 100% reliable ground truth point cloud data from it. Okay. Okay. So how do we do the leveling? So I'm not going into the details of how we do the point sampling and what are things we do actually, but from a user's perspective, so how do we do the leveling? So consider that these are the L string of a geometric plant model. For example, let's say this is I means internal, okay, and this at O means it's a sphere, and leaf is another L string that's defined somewhere, and also some other primitives. Sorry, L strings are there in the model. Okay, so for example, the L string of some geometric plant model is I, then at O sphere, then leaf, and then internal, and then leaf, and some other combinations. That's it. So basically, we need to know what are the L strings of a model. So let's say if you don't know the L strings of a model, you basically print it and then see actually what are the L string models. So here, what are the L strings? Like a unique L strings. So I is there, like at O is there, and leaf is there. So you have 3 L strings in this model. I mean, up to here at least. We assume that the same things are getting repeated in the subsequent L string model as well. Okay. So second, we need a dictionary, so that will actually do the leveling. So how the dictionary will be created? So the dictionary will be created, but basically you put a label to each of the L string actually, nothing else. So that means here, for example, let's say I, so if I put, so here I is 2, so this is like a demo dictionary, okay? So there are other type of L strings as well that's not present in this model. But let's say you are given a universal dictionary like this. Okay. So for example, here I has a level 2 that is assigned to, and at O, so if you see that at O has a level 5, and leaf has a level of 7. Okay, and there are other strings as well, but you can change it. So you can keep the leaf at level 1, O at level 2 and 3, and whatever and so on. But again, like even if you have a level that's starting from 2, so this is 2, and then the O was 5, and then the leaf was 7, but still after simulating the model, so all the levels will start from 1 and it will be consecutive. So that means if you have this dictionary, then automatically I will be assigned as level 1. So at O, that means spheres will be assigned as level 2, and the leaf will be assigned as level 3. So this is basically the sequence of order is maintained, but this relative position is not considered. It's always started from 1, 2, 3, and so on and so on. But you can change the leveling if you want. Okay. But this is like for your own customization. So you can create your own dictionary as according to your application or as you wish actually. But even if you don't create a dictionary, we also provide a default dictionary. So for example, let's say this is a default dictionary, let's say. And if your model already has entries from this dictionary actually, then actually it will automatically create the labels and no problem. But if you have a L string model where some of the L strings are not mentioned in the dictionary, then actually all this will be having a like a default level. For example, let's say if leaf was not defined here, and let's say you have some other levels here as well. So then let's say your default dictionary contains 10 levels. Then if there is a new L string here, so the new L string will be assigned a level 11. So for example, here, let's say you have another level like L string like flower. So flower will also be assigned a level of 11. So whatever new stuff is coming, so that will have the same level. So, but maybe that will not be very appropriate for your application, but actually, but your code will run eventually, and it will give some level. But if you really want to have some customization of the level, then actually you have to write like specify your own dictionary. Either you have to know the L strings, or you just simply print it and then put it in the dictionary accordingly. That's it, nothing else. Okay. Also, you can write your own function for the levels. So how do you generate the levels actually? So this is also possible, but this is for the advanced applications actually, not for the beginners or the naive users. So if you know the geometry model of the plant, then actually you can create the levels using your own function. So in short, given any virtual plant model in LPI environment, it is possible to generate level point clouds from it. So that's it. And then eventually using this technique, actually we can generate level point cloud data. So that means level point cloud means each point in the cloud will have a specific level 1, 2, 3, 4, whatever. And we can assign color according to the level as predicted here. Okay. So here actually after generating the levels and generating the point cloud, sometimes we also have a problem of insightness. So what is insightness? Because for example, we are generating the points at the surface of the plant, right? But so whenever there is a branch actually, so actually in the model, so this branch actually starts from the inside of the plant. So I mean, so the origin of this branch is somewhere inside this hollow part actually of this cylinder. But if you generate sort of sample points, for example, on the surface of the green cylinder, so these points will remain inside the red cylinder. But that doesn't happen in the real plants. Everything is outside or the surface actually. So we also resolve these type of things by doing some testing, like geometric testing, if two primitives are remaining inside or other. So if this happens, then we discard those points actually. So that means if you are requesting to sample or generate 1000 points, so all the 1000 points will be exactly on the surface of the model actually. Nothing will remain inside. So this is explicitly considered in our formulation. Okay. So here are some results. So this is basically a very simple example. So it's just like a simple branch actually, you see. So here actually we are trying to use 3 levels. So 1 level for each branch. So here you see that this red branch actually. So this red color actually we did it intentionally inside the model actually. So that's why just to show the matching actually with the point cloud and the original model. But so this is the original model, which is actually like a computer graphics primitives, and this is actually the point cloud. So you see that the point clouds are sampled, and these sample point clouds are actually remains at the surface. So you see this green part, actually this is not inside, actually this is at the surface, but due to the visualization it looks that it's remaining inside, but everything is at the surface. And also here for this branch as well, everything remains at the surface actually. But this is a very simple example. We can also show some other examples later. So it is also possible to add a very basic noise model. So we have modeled like a very basic noise model. So, but there are some other device-specific noise, and also this type of things are also possible to add. The function is customizable. Okay. So you see that here this is a plain Gaussian noise actually with this, and all the noise points actually they are also labeled. So everything is labeled here. Okay. So also we can customize the noise effect. For example, let's say if your camera is here at the tip. So sometimes what happens in the real laser scanners, so the noise near the camera is very less, and as you go further from the camera, the noise increases. So this type of effect is also simulated here. You see that the noise is pretty low in this area, and actually it starts increasing actually you go further. Actually. So this is a very basic noise model. So we just show that this type of function is available, and you can customize it. So you can customize according to your application or your own noise model. Okay, so this is a real example of Arabidopsis plant, which is like a virtual plant. And these two models, as I was mentioning initially, the stochasticity. So actually, these two are from the same plant model actually. So same geometric plant model. And two instance of launching the program actually gives two different plans. So you see that the branches are basically bending and all these things are happening. So these are all happening due to the inherent stochasticity. So we didn't have to change anything in the model to do this. And if you launch it 1,000 times, then you will get 1,000 varieties actually. And in both cases, so everything is labeled. So we did the labeling here with the 3 labels as before. So this red is the rosette, and green is the stem, and blue the rest of the others. But as I mentioned, you can also customize these things according to your application. So this is also another artificial plant. This is lilac. So here also we label the stem with red and all the flowers with blue. But also again we test it with other things like each flower can have different level as well. Okay, so this is also possible with this type of thing. Okay, so with this completes basically the very basic overview of the methodology or how things are actually done. So now let's see how to use the software library actually. Okay, so basically you go to the folder or directory where actually you have the example or some of the examples are given. So here actually you see the generate point cloud.py. So this file actually, and here actually you see some examples. So some of the examples are given here, and I'm showing you like 1 or 2 examples, and the rest of the things are self-explanatory actually. So how to use these examples? So first you source activate the things as the regular standard procedure. Okay, and then so first of all this Python and then generate point cloud.py. So this is the main sampler file. Okay, so this part is fixed for any type of sampler. Okay, and then basically you specify the model file, the lpy file actually. For example, here this is model1.lpy. Okay, but you can have any other model as well. And then give a space, and then the number of points you want to sample. So this line means, so I'm trying to sample points or label point cloud from this lpy file where there will be 100 points that will be sampled on the surface of the plant. Okay. So here, see, I didn't specify any dictionary. So that means whenever I will launch this code, actually, it will assume that we'll be using the default dictionary file actually that is already provided. So if you go to the directory, actually, you will see that there is a level dictionary.txt. It's already there actually, but we didn't specify this. Okay, so we are basically using the default dictionary that is provided within the code. So you will see that there is a level table. So this is basically the default optional, like a default dictionary that is used basically if you don't specify anything. But here, I mean, if you really want to specify the dictionary, then basically you use the -d flag basically, and by -d, and then if you use __ default and then __, so that means it will be using the default dictionary file. So default dictionary file is also available in the same directory. You can have a look. So basically, where is this is the level dictionary.txt, So you see that this is a default dictionary. There are 17 levels that are given. So this pretty much covers many of the common geometric plan models actually with this L string aspect. But you can customize it, of course. So that means if you specify this actually, so this means it will use the default dictionary model. Also, you can have your own dictionary file. So for example, -d, and then you specify a text file, level dictionary.txt. So that means this will be your own thing like this. Okay. So just for a clarification, so I will show just on the first example actually. There are other type of options also available for launching the code actually, but these are self-explanatory. You can just have a look by yourself. So for example, if I want to have generate a point cloud model of my model.lpy, which is my lpy file, and I want to sample 100 points on the surface of the plan. So I will basically launch this command. Okay, it will take some time, and then eventually it will stop. And then what it will generate? It will generate 3 files actually. So okay. So you see here. So this basically uses a level function for define module level. So these are some messages that are basically shown. Okay, so after it will complete, so I have already pre-computed this. So it will generate 3 files actually. So first the raw point cloud.xyz. So that means this is the point cloud without any level or anything. So you see that x, y, and z. There are 3 columns actually in each line actually, and there are exactly 100 of them. So since I specified 100. Okay, so second one is the levels.txt. So level.txt is basically the level corresponding to the 100 generated points. So you see 1, 1, 1, and somewhere it will be like 2, 3, and so on and so on. So okay, so here only one level is showing because my dictionary was not, my L string was not present in the dictionary. So if you have your customized dictionary that covers all the L strings, then you will see that 1, 2, 3, 4, whatever levels you have. And also third, you will have a colored point cloud.xyz. So that will have like a xyz and then the RGB value actually corresponding to the level that we have. So that means level 1 you can give like a red, level 2 you can give green, and level 3 blue, and so on and so on. So these colors are also generated randomly. You don't have to do it. So basically, if you try to see this in the visualizer, then actually you will see nice segmented ground truth segmented point cloud. So that's all about the model, and you don't need anything else. So there are other examples also available. So you can try these examples on your own. So these are pretty self-explanatory, and that will generate. So it depends on how much time it will take. It depends on the complexity of the model and the number of points you generate actually. So if you try to generate, like for example, like 1 million points, of course it will take a huge time. But usually, like a 10, 20,000 or even 50,000 points for like a small scale plans, it should not take much time if your machine is relatively faster. So that's all about the sampler, and I'm stopping the presentation here.
Thank you very much, Ayan.